So now let us see some properties of electric field lines. Okay, so electric field lines are the lines drawn to show the electric field in some region. Okay, and they are directed along the force acting on a unit positive or positive test charge. Okay, a positive small test charge, not unit, a positive small test charge. Okay, so the electric field lines due to a positive charge, they are directed radially outwards. The electric field lines due to a negative charge, they are directed radially inwards. Okay, let's see some properties of electric field lines. Properties of electric field lines. First one is obvious. They start at positive charge and they end at a negative charge. So they start at positive charge and end at a negative charge. Okay. So then they are dense in the region of strong electric field and they are separated in the region of weak electric field. Okay. So they are more dense in the region of strong electric field and they are separated in the region of weak electric field. Okay, so as electric field becomes stronger, the electric field lines get denser and denser. Okay, and separated in the region of weak electric field. Right. So density of electric field lines tells us about the electric field. Okay. So then at any position in space, if we draw a tangent to an electric field line, it will give us the direction of electric field at that point. Okay, so tangent drawn to the electric field line at any point in space gives the direction of electric field at that point. Okay, so let's suppose we have electric field lines like this. Okay, then if I want to find out the electric field at this point, what will I do? I will draw a tangent at this point. Okay, so electric field at this point is directed like this. If I want an electric field at this point, I will draw tangent at this point. Okay, so electric field at this point is directed like this. Okay, so tangent drawn to the electric field lines at any point gives the direction of electric field at that point. Okay, so that's another property. Let's see property number 4. Two electric field lines never cross each other. Okay, two electric field lines never cross each other. Okay, so why do they don't cross each other? So let's suppose for an example they cross. Okay, so let's suppose these two electric field lines cross. So can you guess why this thing cannot happen? Okay, let's suppose these are two electric field lines. Why this kind of electric field lines are not allowed? It's simple. See, see, at the point of crossing. So see, property number 3 says that tangent drawn to, the property number 3 says that tangent drawn to electric field line at any point gives the direction of electric field at that point. Okay. So now, see, if you draw a tangent to this electric field line, then it will say that the electric field at this point is directed like this. And if you draw a tangent to the other electric field line, it will say that the electric field is directed like this. Okay. But at any point in space, you can have only one direction of electric field. You cannot have two separate directions, right? So this cannot be possible. Okay. Two lines can never cross each other, right? At any point in space, you will have only one direction of electric field, the net electric field. Okay. So these two lines, they are telling that there are these two separate directions of electric field, which is not possible. Right. It will have two tangents, which is not possible. Okay. Very good. All right. Then there is another property. The electric field lines do not form closed loops. The electric field lines do not form closed loops. Okay. So you can draw a pattern of electric field lines anywhere in space. So this kind of an electric field line, this kind of a figure, this is not allowed. Okay, because here you don't know where these electric field lines are originating from and where they are ending at. Okay, so this is not allowed, right? You cannot guess what is the origin. So origin would be some positive charge. Okay, and the end point would be what? Some negative charge. So here you cannot guess what is the origin, what is the end. Okay, so this thing is also not allowed. So these are properties of electric field lines. Okay, key properties. There are others also. And sometimes there can be questions, conceptual question based upon this. So is it clear? So these are properties of electric field lines. Then let's move on to the next topic. Okay. So now we'll keep electric field lines at hold for some time. Okay. We'll discuss uh, electric field due to some other things. And then again we'll come back to the electric field lines. Okay. And we'll understand the Gauss's law. So let's talk about electric dipole. So what does an electric dipole mean? Electric dipole means a positive charge and a negative charge. Positive charge and same amount of negative charge. And there is some distance between these two charges. Okay. So this is plus q and this is minus q, and there is some distance between these two charges, right? So this kind of a system is known as an electric dipole. So for an example, so where do you find these electric dipoles? So you find them in polar molecules. Okay, you know what are polar molecules? For an example, HCl. So how does HCl gets formed? So there is H atom which has very less electron affinity because there is only one electron in its outermost shell. There is only one shell actually, right? There is only one orbit. Okay, and Cl has 7 electrons. So Cl wants one electron and H wants to give that electron to be stable, right? So what happens is an ionic bond gets formed between H and Cl. Okay, so you have H positive atom, okay, ion, and Cl negative ion, right? And how much is charge on them? So this one has plus q charge, charge equal to charge of one electron but positive charge, and because it is giving that electron to Cl, okay, it will have charge equal to what? One electron but negative charge. Okay, so these are two charges, okay, two charged ions, you can say, positive and negative, and there is some distance between them, okay, very small distance between them. So this kind of a system is called as an electric dipole. Okay, so electric dipoles are found in polar molecules, right? All right. So now what we are going to do is we are going to find out the electric field due to an electric dipole. Okay. So for that, let's define one quantity known as electric dipole moment. Electric dipole moment denoted by letter P. P is equal to magnitude of one of the charge multiplied by distance between two charges. Okay. So distance between these two charges, it is written as 2 times A or 2 times D for convenience. Okay, so this much distance is written as 2 times A, and this is the midpoint. So midpoint is suppose O, this is point O. So distance from plus Q to O is A, distance from O to minus Q is also A. So distance between plus Q and minus Q, it is written as 2 times A. So electric dipole moment is Q multiplied by 2A, and we'll see that this quantity, okay, the dipole moment, will come in all the formulae which are related to electric dipole. Okay, so that's why it is important. And this is a vector quantity, so this is magnitude of electric dipole moment. It has got direction also, so its direction is from minus q to plus q. Okay, so p bar is equal to q times 2a or 2qa, this is the magnitude, multiplied by a unit vector in the direction of the electric dipole moment, and it is directed from minus q to plus q. So this is the direction, minus q to plus q. This is convention. The electric field due to an electric dipole at a point at an equator, okay, any point on equatorial plane. Okay, so what is an equator for electric dipole? So this is our electric dipole, charge plus q, sorry, charge plus q and minus q. This is the midpoint, point O. Let's call this point A, this point as B. Okay. So now if you draw a perpendicular bisector to this line, perpendicular bisector to this line, okay, that is known as equator. Now there are multiple perpendicular bisectors that you can draw. Okay. So let's suppose this is the dipole. Okay. Now you can draw a perpendicular bisector like this or like this, like this. All of these are perpendicular bisectors, right? So now if you connect all these lines, what will you get? You will get this plane. Okay. So equator, so there is an equatorial plane. Okay. Any line on that plane can be called as equator. It will be perpendicular bisector for this dipole, right? So let's consider one such line. Let's consider one such line. Okay, so then this is point P where I want to find out the electric field due to this dipole. So we'll join point P with positive and negative charges. Electric field due to positive charge, it will be directed radially outwards. So this is electric field due to positive charge. Let us call it E plus, plus for positive. And electric field due to negative charge, it is directed radially inwards. So let's call that field E minus. Okay, let's call that field E minus. Okay, and let's suppose this much distance is R. Okay, distance of that point P from midpoint of the dipole is R. So now the point P is at same distance from plus Q as well as minus Q. Okay, this distance AP and BP would be equal, right? Because if you consider this triangle and this triangle, they are equilateral triangles. Okay, because see, this distance is equal to this distance. This side is common, and this angle is 90 degrees. So by SAS test, we can say these are congruent. Okay, so this and this distance is equal, right? So since uh, the point P has is at same distance from plus Q and minus Q, we can say that the magnitude of electric field due to plus Q and minus Q at that point would be equal. Okay, so we can say magnitude of, this is E plus bar, this is E minus bar. So E plus is electric field at P due to plus Q. E minus is the electric field at P due to minus Q, and since the point P is at same distance from plus Q and minus Q, we can say that the magnitude of electric field due to plus Q is equal to magnitude of electric field due to minus Q, and let's suppose it is equal to some E. Okay, now what would be the net electric field? So net electric field due to the dipole, let's call it E net, it's just vector sum of the electric field due to positive charge plus electric field due to negative charge. Okay, so this is principle of superposition, right? So principle of superposition says force due to net force at any charge, sorry, net force acting on any charge kept in space is equal to what? Sum of a vector sum of all individual forces. So since net force is vector sum due to all individual forces, okay, net force is equal to vector sum of forces due to uh, all charges, we can say, and therefore net electric field would be vector sum of the electric field due to all charges. So here we have only two charges. Okay, so now what would be the direction of that net electric field? It will be directed like this. Okay, so if we draw a parallelogram like this here, then using parallelogram law of vectors addition, we can say that the electric field, net electric field, will be directed along the diagonal of that parallelogram. Okay, so it will be directed like this, right? So let's find out that. Okay, so for that, what we are going to do is we'll consider that this angle is equal to theta, right? So this angle will also be equal to theta. Okay, because two triangles are congruent, and this will be 90 minus theta. So since this is 90 minus theta, we can say that this angle is equal to theta, and since this is theta, this angle will also be equal to theta. Okay, or you can say uh, these are two parallel lines. This is an intercept. So these are alternate angles. So they will be equal. Okay, and again these are two parallel lines. Okay, this is an intercept. These are corresponding angles. So they are also equal. Right. So this angle is also equal to theta. Okay, and then we can resolve E plus bar and E minus bar along two perpendicular components. So let us do that. Let's resolve E plus bar and E minus bar along two perpendicular components. Sorry. Okay. So this component of E plus bar will be what? E sine theta. Okay, so this is E plus sine theta, you can say. This component due to E minus bar would be E minus sine theta. Okay, so this is E minus sine theta, right? So vertical components or components along the equator, see they are directed opposite to each other. Okay, and since E plus bar, the magnitude of E plus bar and E minus bar is equal, so this is E plus sine theta, this is E minus sine theta. They have equal magnitude and they are directed opposite to each other. So they cancel out, right? And these components, component in horizontal direction, they will have this much magnitude. Okay, so this is, let's suppose, component due to E plus bar. So it is E plus cos theta. And there will be one component of same magnitude, it is E minus cos theta. Okay, we can draw it here of same length. So this is E minus cos theta. So E plus cos theta and E minus cos theta, they are directed in same direction. Okay, so they get added, and therefore net electric field is this much. Net electric field is this much. Okay, so we can say magnitude of net electric field is equal to what? It is equal to E plus cos theta plus E minus cos theta, right? And the magnitude of E plus bar and E minus bar is equal. So we can say this is equal to 2 times E multiplied by cos of theta. Okay. Then, now how much is E? So E is the magnitude of electric field due to plus Q or minus Q, we can say. So see this distance, let's call it R plus. Okay. So can you see this diagram, or there are too many things? Okay. So let's suppose this distance is R plus, this distance is R minus. So R plus is equal to R minus. Okay. So I can write that it is 2 times E. E is equal to 1 upon 4 pi epsilon naught multiplied by, we want magnitude only. So it is Q divided by R plus square or R minus square. Okay. So let's write AP square. Okay. And if we see this triangle APO, then cos of theta is this distance QO divided by AP. Okay, cos of theta is QO divided by AP. Okay, so it is, how much is distance QO? This distance is equal to A. Sorry, I'm saying QO, it is AO. I'm sorry. Okay, distance AO divided by AP. Okay, Q is the charge, right? So it is 1 upon 4 pi epsilon naught multiplied by 2Q divided by, we have AP cube in the denominator. This AP cube, or let's do one thing. Let us call this distance as x. Okay, distance of point P from the center of the dipole, let's call it x, and let's call this distance as r, which distance AP is equal to r. Okay, all right, and so I can write that it is equal to, I will put r in place of AP, so this is r cube multiplied by distance AO. So what is AO? This distance is equal to small a. Okay, half of the length of dipole. Okay, so can you see that there is 2 times QA in the numerator? And what is 2 times QA or Q times 2A? It is the electric dipole moment. Okay, so we can write 1 upon 4 pi epsilon naught multiplied by P upon R cube. And what is R? This distance is R. So if we consider this triangle, R square is equal to A square plus X square, we get. Okay, so R square is equal to A square plus X square. So how much would be R? R is equal to A square plus X square raised to 1 by 2. Okay, square root of that. Okay, and we have third power of R here. So we can write it is equal to 1 upon 4 pi epsilon naught multiplied by P divided by R square, sorry, A square plus X square raised to half raised to 3 is raised to 3 by 2. Okay, this is E net. Okay, or we can call it E equatorial. Okay, so E, let's call it E equatorial, EEQ, because E net is, we are finding it on equatorial plane. So E equatorial, the electric field on equatorial plane of a dipole is equal to 1 upon 4 pi epsilon naught multiplied by P divided by R cube. And what is R? It is square root of A square plus X square. Okay, R is equal to square root of A square plus X square. Now this is the formula for, this is the formula for the electric field. Okay, this is the magnitude. What will be its direction? So see, its direction is like this. Okay, so if we consider the direction of the electric dipole moment, it is from minus Q to plus Q. Okay, electric dipole moment is directed from minus Q to plus Q. This electric field is opposite to that. Okay, so if I want to write it in vector form, I can write it in vector form. The electric field along equator, E equatorial bar, is equal to 1 upon 4 pi epsilon naught minus P bar divided by R cube. Minus P bar divided by R cube. Is it clear till this point? Now let's consider a special case. Okay, so what is a special case? So we saw what is an example of electric dipole. So it is, mostly we talk about electric dipoles in terms of polar molecules. And what is size of a molecule? size of molecule is about 10 raised to minus 9 meters. Okay, 1 nanometer or something. It is of that order, right? Okay, 10 raised to minus 8, 10 raised to minus 9 meters. Okay, so it's very, very small. Okay, so length of the dipole is very, very small, and the distances at which we want to find out their electric field is very large compared to their length. Okay, so that is the special case. Okay, so we often require that A is very, very small compared to X, we can say. Okay, what is X? Distance of point P from the midpoint of the dipole. So length of dipole is very small compared to this distance. Okay, so if A is very, very small compared to X, then we can say that E equatorial is equal to 1 upon 4 pi epsilon naught multiplied by P divided by X cube. Okay, because what is R cube? R cube is equal to X square plus A square raised to 3 by 2. So if A is very small, we can neglect it. So A square will be very, very, very small compared to X square. We can neglect it. So it will be X square raised to 3 by 2. That means X raised to 3. Okay. So this is applicable only when length of the dipole is very small compared to the distance where we want to find out the electric field. Next, let us see electric field due to a dipole at an axial point. So let's consider a dipole. So this is an electric dipole. Charge plus Q and minus Q. And what is an axial point? So axial point is any point along the line joining these positive and negative charges. Okay. So let's suppose this is the point where we want to find out the electric field. This is the point P. Okay. And it is at distance x from the center of the dipole. So this is point O, this is A, this is B, and this much distance is equal to what? This much distance is x. Okay. So now see what will be the direction of electric field at this point due to positive charge. It will be radially outwards from the positive charge. So it is towards point P. Okay. And what will be the direction of electric field at this point due to the negative charge? It will be like this. Okay, towards point Q. Okay, that means if you keep a positive charge over here, it will be repelled by positive charge and it will get attracted by negative charge. Okay, but whose electric field is more? Because this point P is closer to the positive charge than the negative charge, the electric field due to positive charge is more. Okay, and that's why if you find out net electric field, so field due to positive charge is like this, field due to negative charge is directed in opposite direction. If you add them, the net electric field will be directed like this. Okay, so that means in what direction? So electric dipole moment is directed from minus q to plus q. Net electric field is also directed like this in the same direction. So electric field now it is directed in direction of the electric dipole moment. Okay, so that was not the case in case of electric field on an equatorial point. So here electric field is directed opposite to the electric dipole moment, and here electric field will be directed in direction of electric dipole moment. Okay, so that is one difference between electric field of a dipole at an equatorial point and an axial point. This is clear. Then once again, let's suppose E plus bar is electric field at P due to positive charge plus Q, and E minus bar is the electric field at point P due to minus Q. So net electric field at axial point, let's call it E axial, E axis bar, it's equal to what? E plus bar plus E minus bar. Okay, vector sum of the two electric fields. Now E plus bar would be more compared to E minus bar. Okay, so let's write down what is E plus bar and E minus bar. So E axial is equal to, what is E plus bar? 1 upon 4 pi epsilon naught multiplied by Q upon distance of that point from plus Q square. Okay, so we know distance from the midpoint of the dipole to the point P is equal to x. Okay, this much distance is x. So how much would be distance from plus Q? This distance would be this distance minus this much distance. Okay, this much distance minus this much distance. Okay, that is distance of point P from plus Q. So it is x minus a. So we can say it is x minus a square. So this is the magnitude. What about direction? It is directed in direction of P cap, okay, or P bar we can say, along the dipole. Okay, then plus, this is electric field due to positive charge only, plus we have electric field due to negative charge. It is 1 upon 4 pi epsilon naught Q upon distance from negative charge square. Okay, so I am just writing magnitude right now. So how much is that distance? It is this much distance we want. So it is equal to this distance plus this distance. So it is, okay, x plus a. It is x plus a square, right? So this is just magnitude. And what is direction? It is directed opposite to the electric dipole moment. So I will just write p cap and put that negative sign here. Okay, we can put it anywhere, right? Then we can take something common. We can take q upon 4 pi epsilon naught, q p cap divided by 4 pi epsilon naught common from these two. So it is q p cap upon 4 pi epsilon naught. We have taken common from these two, and we have 1 upon x minus a squared minus 1 upon x plus a squared. We can make denominators. We can make denominators of these two terms same. So we'll multiply this one with x plus a square, and we'll multiply this one with x minus a square. So what do we get? We get qp cap divided by 4 pi epsilon naught multiplied by, you have x plus a square. We are multiplying first term by x plus a square and second term with x minus a square. This is x minus a square multiplied by x plus a square in the denominator, and in numerator we'll have x plus a square minus x minus a square. Okay, then we can expand this x plus a square and x minus a square. So what do we get? qp cap divided by 4 pi epsilon naught. So this is eaxis. So x plus a square is x square plus 2 times x multiplied by a plus a square. Okay, and x minus a square is x square minus 2 times xa plus a square. Okay, and in denominator we have x minus a square multiplied by x plus a square. We can say it is square of x minus a multiplied by x plus a. And what is x minus a multiplied by x plus a? It is x square plus a, sorry, x square minus a square. It is x square minus a square. We have square of that. Okay, x minus a multiplied by x plus a is x square minus a square, and we have square of that. Okay, and then what will happen? This x square and minus x square gets cancelled, a square and minus a square gets cancelled, and we are left with 2xa minus minus plus 2xa, so that is 4xa. Okay, so we are left with eaxis bar is equal to, okay, and of course p cap, sorry, p cap I have written. Okay, so it's equal to qp cap divided by 4 pi epsilon naught x square minus a square, square of that, and in numerator we have 4xa, 4xa, right? And once again we'll write this as 1 upon 4 pi epsilon naught multiplied by, we'll write this as 2 times 2qa or q into 2a. Okay, multiplied by p cap multiplied by x. So I have just written this 4 as 2 times 2. Okay, so it is 2 times 2 qa multiplied by this x. Okay, and p cap. And in denominator you have x square minus a square, square of that, right? So what is q times 2a? It is electric dipole moment. So we have electric dipole moment multiplied by p cap. Okay, magnitude multiplied by unit vector in that direction. So it is 1 upon 4 pi epsilon naught multiplied by 2 times p bar into x divided by x square minus a square raised to 2. So this is electric field along the axis. Then once again we will consider the same case. Okay, what same case? Same special case that the length of dipole is very small compared to the distance of that point from the center of dipole or midpoint of dipole. So if it is so, then we can neglect this a square in comparison with x square in the denominator. Okay, so it is x square square, that is x raised to 4. Okay, x raised to 4, and then in numerator we have x. Okay, so we can divide by that x, or this x raised to 4 to this x raised to 4, so we get x raised to 3. Okay, so it is e axis is equal to 1 upon 4 pi epsilon naught multiplied by 2p bar I'm sorry, 2p bar divided by x raised to 3. Okay, so this is what is left. And here we can see that electric field due to axis is along the electric dipole moment. Okay, so E axis is parallel to P bar, right? E equatorial is opposite to P bar, or you can say anti-parallel to P bar. And if you talk about the magnitude, so see, we are generally concerned with large distances. Okay, when distance is very large compared to length of the dipole. So then approximate formula is this one. Okay, for E axial, and for E equatorial, the approximate formula is this one. Okay, so then you can say that E axis is equal to what? It's 2 times of E equatorial in magnitude. So this is electric field due to dipole at an axial point and an equatorial point. Okay. Now let's see electric field due to dipole at any point in space. Let's draw a dipole. This is a dipole, suppose, and this is minus q, this is plus q, and we want electric field due to this dipole at this point. Okay, we want electric field due to dipole at this point. Okay, and we'll consider that length of the dipole is very small compared to this distance. Okay, compared to x, this distance. Okay, so now what we can do? So we know the formula for electric field due to dipole at axial point. We know the formula for electric field due to dipole at an equatorial point, and electric dipole moment is a vector quantity. Okay, P bar is directed from minus q to plus q. So we can resolve this vector along two components, two perpendicular components. Okay, so what we can do is we can resolve this vector along two perpendicular components. So see, this angle is suppose theta. Okay, so we'll resolve this dipole moment itself along two components. So see, this much is length of the dipole. We'll draw a perpendicular uh, on this line, which is perpendicular to OP. Okay, so let's draw a perpendicular like that. So it would be this much. If we draw a perpendicular, okay. So if this dipole has a dipole moment equal to P bar, so this dipole has dipole moment like this equal to P bar. Now this is one component of the dipole moment, and there would be another component. Another component would be directed like this. Okay, we are resolving another component would be this much, right? Okay. So what we are doing is we are resolving this p bar along two perpendicular components. So this angle is theta. Okay, so this angle is theta. So this component would be p cos theta, and this component would be what? P sine theta. This component is p sine theta, right? So now see, these are like two dipoles. Okay, one dipole is directed like this. Its dipole moment is p sine theta, and one dipole is directed like this. Its dipole moment is p cos theta. So for this dipole, let's call it perpendicular dipole, p perpendicular. Why perpendicular? Because this dipole moment is so this point P is an equatorial point for this dipole. Okay, that's why P perpendicular. And let's call this one P parallel. Okay, which one? This dipole is P parallel. Okay, why parallel? Because this point is along the same line as that of this dipole. Okay, so we can think of these two separate dipoles. They are producing some electric field at that point P. Okay, so what we are doing is we resolve P bar along two perpendicular components, P perpendicular and P parallel. Okay, so now how much would be the electric field at point P due to P perpendicular? So electric field at point P due to perpendicular component of electric dipole moment, P perpendicular. So this point is this point is this is P perpendicular, right? So this point is an equatorial point for P perpendicular. So we know electric field along equator. Okay, so let's call it E perpendicular. It is equal to 1 upon 4 pi epsilon naught multiplied by P perpendicular divided by distance square. How much is distance? X. So x square. Okay, is it x square? Sorry, it's x cube, not square. Okay, and electric field at point P due to electric field at P due to this P parallel, let's call it E parallel, it will be equal to what? 1 upon 4 pi epsilon naught multiplied by 2 times P parallel upon x cube. Okay, because for this one, for P perpendicular, it is an equatorial point. So electric field is 1 upon 4 pi epsilon naught P upon x cube, right? And how much is P? It is P perpendicular. Okay, and then for this dipole, this is an axial point. So electric field is 1 upon 4 pi epsilon naught 2 times P, 2 times the dipole moment. Okay, P parallel upon x cube, right? And in what direction is the electric field directed? So E parallel would be directed like this, and what will be direction of E perpendicular? So this is the perpendicular component. Okay, so perpendicular component is directed like this. Perpendicular component of dipole moment is directed like this. The electric field is opposite to that. The electric field is opposite to that. Okay, these two components of electric field, they are at right angles to each other. So how much would be net electric field? So therefore net electric field would be vector sum. Sorry, it is field would be vector sum of E perpendicular and E parallel. E net is equal to E perpendicular bar plus E parallel bar. Sorry, it is E parallel bar, right? And see, they are directed at an angle of 90 degrees to each other. So what would be the magnitude of net electric field? It will be, so we can say net electric field square would be E perpendicular square plus E parallel square. Okay. And how much is E perpendicular? E perpendicular is 1 upon 4 pi epsilon naught P perpendicular upon x cube. 1 upon 4 pi epsilon naught P perpendicular divided by x cube. Plus you have square of this plus 1 upon 4 pi epsilon naught multiplied by 2 times P parallel divided by x cube. And we have square of this one also. Okay. This is E net square. We want square root of that. Okay. So we want E net, which would be square root of that. This is square. So what I will do is I will take 1 upon 4 pi epsilon naught x cube common from these two. So if I do that and take square root, so I can write E net, the net electric field due to dipole at any point would be 1 upon 4 pi epsilon naught 1 upon 4 pi epsilon naught multiplied by 1 upon x cube, and here we'll have P perpendicular square plus 2 times P parallel square. Okay. So see, then how much is P perpendicular and P parallel? Okay. So what I have done in this step, I have just taken square root of this right hand side and taken 1 upon 4 pi epsilon naught upon x cube common from these two. So we have square of that and square root of that. Okay. So 1 upon 4 pi epsilon naught multiplied by 1 upon x cube I have taken out, and there will be square root of remaining things. So which is P perpendicular square plus 2P parallel square. We have square root of that. Okay. Yes, no? Is there any question till this point? Any question? Okay, good. Then what is P perpendicular and P parallel? So P perpendicular, okay, is dipole moment of this thing. It is P sine theta. It has P sine theta, right? And P parallel is dipole moment of this thing. I should have written it like this. Sorry, dipole moment of this dipole. It is P parallel equals to P cos theta, right? So P parallel is P cos theta and P perpendicular is P sine theta. Let's substitute that. So we get E net is equal to 1 upon 4 pi epsilon naught multiplied by 1 upon x cube. So here we have square root of P sine theta square plus 2 times P cos theta square. Okay. And then we'll have P square from here, P square here also. We can take it outside of square root. So it is 1 upon 4 pi epsilon naught multiplied by P upon x cube. Then we are left with square root of sine square theta plus here it will be 2 cos theta square. It is 4 cos square theta. 4 cos square theta. Okay. And then we'll take one of these 4 cos square thetas. Okay. So cos square theta plus sine square theta is 1. Then we'll be left with 1 plus 3 cos square thetas, because we have taken one of those 4 cos square thetas, okay, and added it with sine square theta, right? So E net would be equal to 1 upon 4 pi epsilon naught multiplied by P divided by x cube multiplied by square root of 1 plus 3 cos square theta. So this is the formula. So this is the formula for the net electric field at any point, okay, at any point due to an electric dipole. Is it clear? Yes, no? Okay. So this formula is clear, right? So how much, sorry, what is theta? Theta is angle between the line joining center of dipole to that point P, okay. So line OP and the dipole moment. It's the angle between them, okay. So let's check whether this formula is correct or not. So for an equatorial point, what would be theta? Theta would be 90 degrees, right? So what is cos of 90? Cos of 90 is 0. So this thing will be 0. Square root of 1 is 1. So see, we get back the formula for E equator. Okay, it is 1 upon 4 pi epsilon naught P upon x cube, right? When theta is 90 degrees for equatorial point, we get E equator. We have theta equals to 90 degrees. We get E equator equals to 1 upon 4 pi epsilon naught multiplied by P upon x cube. Okay, this is no surprise because we used that formula to find out this one, right? And for axial point theta equals to 0 degrees. So substitute that. Cos 0 is 1. We have cos square theta, which is 1. 3 times 1 is 3. 3 plus 1 is 4. Square root of 4 is 2. Okay, so we get back this formula. E axial or E axis is equal to 1 upon 4 pi epsilon naught multiplied by 2p divided by x cube, right? So this is just check. Okay.